Okay, this number is ever changing because as the reaction goes on, over time the reactant concentration changes. But that is a constant. It was what the reaction, the concentration was at the beginning. And that's equal to negative kT. Remember what K is. K is that rate constant. The value of K tells us how fast the reaction is. All right, so taking it over here. I took that ln of the concentration of the reactant initially, and I moved it over to the other side because over here on the left side it was being subtracted. I just added it to both sides. The negative kT is still there on the right. Move that over. K is the rate constant. The initial concentration, that's a constant too. So the relationship as time changes, how is the natural log of the reactant concentration changing? There's a relationship there. There's a rate relationship there. If we were to plot the natural log of N2O5 versus time, given that K and that term are constant, what would you get? It would be a straight line, wouldn't it? Because if we called this term y and that t term x, y equals a constant times x plus a constant. That is the form of an equation of a line. Yeah? All right. So K would represent the slope of the line. Remember, K tells us how fast the reaction is. The bigger the slope, the faster the reaction. And then the natural log of the N2O5, that term right there is the y-intercept. I mean, that's some non-zero number. Now, it was important to notice that this was true only because this is a first-order reaction. I did, and I'm going to just change the slide for a second on you. I told you it was a first-order reaction, and because of that first-order reaction, we had that first power there. So when it integrated, it mattered that the N2O5 concentration was to the first power. So this is only good when the reaction is a first-order reaction in the reactant concentration. It's only good for first order. And here's really the punchline of it in red. If you plot on a graph the natural log of the reactant concentration versus time, if it gives you a straight line, that means that the reactant was first order. All that for that. That's it. So if I give you a reaction and say, okay, here's a reaction, let's run it. And we measure the concentration of the reactant and over time. How is the concentration changing over time? That's what we're going to do on Monday. I'm going to ask you, what is the order of the reactant? It's either zero order, first order, second order. It's one of those three. You have to, if you want to know if it's first order, you have to take all that data, and for every concentration that you measured, you have to take the natural log of it and plot it versus time. And if that plot gives you a straight line, then that means it was first order. There's no other way to tell if it's first order. You've got to do that silly plot. Okay? What if it's not first order? What if you plot this thing out and gives you a curve? Well, it wasn't first order. We know that. And can we tell which order it was between the zero now and the second? Well, yes, we can. I'm glad you asked. So here's another reaction. Let's say that we have some reaction, A yields B. And it's a second order reaction. All right. That means this. We can go through the derivative again if you want to. We don't have to. I said the derivative. It was the integration. This is a differential equation. That's why I said the derivative. It is actually integration of that equation. But you're going to choose not to. So I'm just going to give you the punchline here before I even give you the joke. Okay? If you love calculus, you can do this yourself. Put the dA over dt on there and get all the a terms on one side, the rest on the other side, integrate. And you're going to get this. If it's second order, notice that exponent on the reactant concentration. Before it was a 1, now it's a 2. That changes the integral. And now we find this. 1 over the concentration of A is equal to positive KT. Remember, the last time it was negative, this time it's positive, plus 1 over A0. If it's a second order graph, or a second order reaction, if you plot the 1 over the concentration versus time, you'll get a straight line. Because that number, again, is a constant, and that number is a constant. So we unfortunately do have to take the inverse of every reactant concentration data point, and you have to take the inverse of it and then plot it versus time. So if the inverse of the concentration versus time is a straight line, that means it was second order. So we want to know what order the reactant is. And you might be wondering, who the heck cares what order it is? Well, yeah, it does matter. We have to be able to write the rate law for a reaction, so that means we got to know what order it is. So to find out the order, you got this concentration versus time here. Take the natural log of the concentration versus time, plot it. If it gives you a straight line, you know it's first order. If it's a curve, then you got to try the other plots. Well, plot the inverse of the concentration versus time. And if that's a straight line, that means it was second order. What if that's a curve? Well, you could probably assume that it's zero order because that's the only other choice. But zero order is going to be on the next slide. When you have a zero order reaction, that means K times A to the 0 power. It means that A's concentration does not affect the rate. So if we were to work this out and integrate, we would get this. The concentration of A equals negative KT plus the concentration initial. So if you plot the straight up concentration versus time, that's probably the easiest one to do first because you already have the concentration versus time. Just tell your calculator to plot it. And if that gives you a straight line, that means it was zero order. It's got, you have to do this to appreciate. You're all looking at me like, when is it 2:09? I've been waiting for this for like 15 minutes. You won't mind doing these. Now, I do want to tell you this. If you have a graphing calculator, it's very handy for these problems, only because if you know how to graph with it, you can do it very quickly. Now, if you don't have a graphing calculator, don't run home and tell your mom, oh, I need $100 so I can go buy a graphing calculator, else I'm dead in chemistry. That's not true at all. It may help you to go through the problems faster for homework, but on the test, on this chapter, I am not going to ask you to make a graph. First of all, we don't have enough time because it does take a long time. But I'm not going to cause you to be at a disadvantage because you didn't go out and spend the $100 on a graphing calculator. So I would say graph them if you know how. Unfortunately, I can't give you any help with the graphing on a calculator. I've never learned how on those TI calculators. I just don't know how to do it. But you will. How many people know how to graph on their calculator? Does anybody not know? Okay, thank you for saying that. So Emily says she doesn't know. Maybe somebody can help her. Emily, would you mind helping Emily? No, you don't want to? So seriously,
I don't know where the high button is.
we can figure that out. If you were to do the homework problems and you had a computer and you just did it in Excel, that would be faster. I'm going to have computers out when we do the lab on Monday because you have to run a reaction. You have to figure out what the order is by making the 3 graphs. It's part of your lab report. Lauren?
I know you can rent graphing calculators in the library too. For
We just go ahead.
Of 2 weeks, then you have to renew it.
We just got a note from Mrs. Isaac. I think it was yesterday. Said I'm out of calculators.
Oh.
tell your students, she said. And I deleted, like, okay, whatever. But now I guess it would have been good to know that. Yeah, so,
Just graph it on
that's
Desmos.
Yeah.
what?
Just graph it on Desmos. It's like it's on online, so if you have like
Oh,
a phone.
I've never even heard of that. So.
It's just the graph.
I was a math minor too, but that was back when we were just using like little calculators. So, okay, so yeah, seriously, these are not going to be terrible problems at all. Yeah, if there are computer apps and programs that you can use and download, man, it will not be a big deal. It's a little bit tedious. I mean, it takes more time than typical problems do, but it's not bad. It's not bad work at all.